All right, thanks for coming, everyone. Today we have the pleasure to have Michael, who did his PhD in Humboldt University under the supervision of Dirk Kramer. He spent 3 years in Amsterdam as a postdoc before joining ETH Zurich at the Institute for Theoretical Studies. And recently he's joined the Perimeter Institute as junior faculty. And Michael will tell us about constraining moduli space cohomology by counting graphs.
Thank you very much for the kind introduction. So it's of course a pleasure to speak here today. I'm going to talk about a bit about moduli space cohomology, and this is supposed to be like an overview talk of the story. So I'm going to give like a broader overview of the main players and of the motivation to study these kind of problems. So here, or at least in this talk, I'm going to focus on the motivation from the modular space of curves. So this modular space is a very classical object. It has been studied like for 150 years and more, starting with the works of Riemann. So one way to think about it is, so this is Mg, and this is like the modular space, or the space of all surfaces that are compact and connected with a complex structure on them. And we fix the genus of the surface. So small g is just the genus of the surface that we want to study. Equivalently, we can also think about this as not the space where each surface has a complex structure, but a hyperbolic structure, so a hyperbolic metric. And this is a viewpoint that physicists very much like. This modular space can also be thought of as the configuration space of two-dimensional quantum gravity. So the metric gives the space-time structure on the surface, on the two-dimensional surface. Here I'm going to talk about the cohomology of this modular space. So and I'm mainly going to talk about cohomology with rational coefficients. Yeah. So this is all rational coefficients. So if you don't know what cohomology means, it's or if you want a reminder, it's roughly these. So these are all vector spaces in this case with rational coefficients, and the generators of these vector spaces, they kind of correspond to holes in this modular space, and they are graded by their degree, and the degree corresponds to the dimension of these kind of holes. Speaking of dimensions, so what is known about this modular space and its cohomology? So the cohomology is some aspect of the topology of this modular space. So, but geometrically, one can already say what the dimension is. So the dimension of mg is 6g minus 6. And this is already an interesting result that you can figure out. And that has been figured out by Riemann in his PhD thesis in, I think, 1857 or so. But from the perspective of topology, this modular space wants to be a lower dimensional space. So that means that these cohomology groups, they are 0. So this space does not have like any cohomology, any holes of dimension larger than actually 4g minus 5. So the topological dimension of this modular space is smaller than the actual dimension. And this is a key result by Hara in 86. So besides this, there's not so much other stuff known about this cohomology. The main result, and this has been a very big result, one of the big results of the last 20 years probably, on the, at least in this field, on the stable cohomology of this modular space. So this is a so-called stable cohomology. And this is due to Madsen and Weiss. But many other people have contributed to this. So there's a proof based on homotopy theory and the technique. And for instance, Tillman pioneered this approach. But they proved, translated to this language here, that if the degree of the cohomology, so if K is small in comparison to G, so if we look into holes that have very low dimension compared to the genus, to the total dimension, so explicitly if 3K is smaller than 2G minus 2, then this cohomology stabilizes. So we can replace these K cohomology groups or vector spaces with kind of a placeholder for G to infinity. And the result by Madsen and Weiss, it shows that this stable cohomology of the modular space of curves is entirely generated by a polynomial algebra in the so-called kappa classes. So these are all polynomials in some kappas, where kappa I is living in some even degree, and the degree is 2 times I. So this is kind of these even degree classes. These are these kappas. And before the pandemic, so before 2021, this was like almost everything that was known about the topology or the cohomology of this modular space, roughly. So maybe 99.9%. The kind of other interesting, so at a kind of complementary direction, there's been a computation of the Euler characteristic. Of this modular space. So the Euler characteristic is just the alternating sum of the Betti numbers, meaning the dimensions of these cohomology groups, or in this case, just the vector spaces. So we just take the sum and we alternate over all the dimensions, and we get the Euler characteristic. And it's another very nice theorem by 86 by Hara and Sergi, who gave a formula for this Euler characteristic. And they also showed that for large G, so for G to infinity, this Euler characteristic grows quite rapidly in magnitude, and it alternates. So they've shown that there's a sign with G, and then the growth rate is modulated by some constant A and another constant B, and then there's a super exponentially growing factor that goes like G to the power of 2G. And these constants here, A and B, they're explicit in their formula, but I don't want to write them down explicitly here. And I want to mention, so because this is about combinatorics, so here already that like key to this result by Hara and Sergi is a combinatorial formula for who computed the number of ways you can glue the edges of an n-gon together to get a surface. So they took some n-gons like this, and they counted the number of ways to glue together like non-adjacent sides of this n-gon. And if you do this, you get a surface. And the Hara and Sergi, they derived a formula for the number of these kind of surfaces that you can get by gluing the sides of an n-gon. And they also kept control on the genus of the surface that you get. And this kind of formula is like a key step here in the derivation of this Euler characteristic formula. But this formula here, it now sets up a very interesting question. So this shows the Euler characteristic is growing quite rapidly, at least in magnitude, of course, only. And it's alternating in sign. So that means two things. So first of all, it also means that the total dimension of these cohomology groups, it also grows quite rapidly, because this is an alternating sum, and an alternating sum gives also a lower bound on the total sum. So we know that the total dimension of the cohomology, it also grows rapidly, and it grows at least as much as the magnitude of this sum, of this super exponentially growing term. And it also shows us that many of these terms here have to be negative. So there has to be lots of stuff going on in odd degree, so for odd k. And we already learned here that the degree of these stable classes is always even. So this also shows us that there's like lots of stuff going on outside of this stable range. And to make things worse, or better, depending on how you see it, you can ask, okay, what can explain like this rapid growth rate of the Euler characteristic? And you can say maybe we can just look into all the stable cohomology here and at least get some partial explanation of this growth rate. But the answer that you get if you look into this more closely is that the dimension of the stable cohomology grows much slower than this huge growth rate of the Euler characteristic. How does this work? So you can estimate the dimension of such a polynomial algebra, let's say, on these kappas. And if we restrict to a specific degree, say the degrees has to be 2k, it's easy, so we have like all the kappas here, it's easy to see that this dimension is equal to the number of integer partitions K. And it's a classic theorem by Hardy and Ramanujan that this number of integer partitions, it grows like some constant to the power of square root k. So the dimension of the stable cohomology, it actually grows less than exponentially. And it definitely does not grow super exponentially like this, this g to the power of 2g term. So the stable cohomology, unfortunately, only explains a very tiny fraction of the total cohomology. So yeah, so this is a puzzle because we kind of have this space, and we know because of the Euler characteristic that there's a lot of stuff going on, but there's no construction or explanation why there's so much cohomology and why these spaces are so complicated. And for this reason, yeah, people have looked into this quite intensively, but the explicit computations before the pandemic, they only proved the existence of 4 other classes outside the stable range. And these were like very complicated computations by algebraic geometers. So only 4 unstable classes were known before 21. And so Benson Farb, for instance, dubbed this then the dark matter problem of the modular space cohomology. So physicists always like this analogy when I give such talks because, of course, dark matter is amazing. But here the analogy is, of course, that we can detect this via the Euler characteristic, but we don't really know what's precisely going on in these cohomology groups. And this is the mystery. So now this changed in 21. So in 21 there was a theorem by Changelacius and Payne. Oops. And they proved that there's an object called Koncevich's commutative graph complex, whose homology injects into the cohomology of the modular space of curves. So this, they proved this injection. So this is an injection. So everything that you find here gives you also a cohomology class over here. And this GCG object is Koncevich's even commutative graph complex. But yeah, you can also forget these 2 adjectives and just think about it as a graph complex for now. And yeah, so this is so they kind of access this combinatorial world of this graph complex to say something about this problem on the modular space cohomology. And this graph complex is now an entirely combinatorial object. So I'm going to explain you now what this graph complex is. So this graph complex is also just a vector space. Say over the rationals. And it's generated by pairs G and sigma. Or let's say gamma and sigma. So gamma is a graph. That is connected it has rank G. That means that the first Betti number of the graph, gamma, is equal to G. And because the graph is connected, this is also equal to the number of edges of gamma minus the number of vertices of gamma plus 1. So this is a nice invariant of the graph that also comes from the Euler characteristic of the graph. And we want the graph to have minimal vertex degree larger than 3. So the vertices have to have degree at least 3 of these kind of generators. And now what is sigma? Sigma provides a way to define like an orientation on a graph. So it's very intuitive to think about an orientation on a surface or on a manifold, but on a graph there's no natural way to define like an orientation. And in a way, this innovation by Kontsevich was to figure out like a good way to define some orientability notion on graphs, such that you can write down such a complex. So if you're not familiar with algebraic topology so much, you have to. So in algebraic topology, it's like combinatorics, but you always need some signs because there's always this orientability problem. So signs and algebraic, so it's like algebraic topology is combinatorics plus signs. In a way. So what is this orientation? How does it look like? So one way to think about it is that it just provides a numbering of the edges. So we have a bijection that assigns integer labels to all the edges of our graph. But then we also want to mod out by some relations. And the relations are very simple. We take for each such pair and some permutation of these edge labels of the graph. We want to have the graph with the permuted edge labels. So this pi then permutes the edge labels of our labeled graph in this pair. And we want this to be equal to the unpermuted case, but we want to pick out the sign of the permutation. So whenever we flip edges or flip the numbering of two edges, we pick up a sign. Here's an example. All right, actually, I start with a non-example. Take this graph here, and we assign numbers to all the edges. And then we are allowed to use the relation. So we change 1 and 2. So we pick up a sign, minus. But this graph is obviously isomorphic to the one we started with. So this is equal to minus this one here as well. So this graph is 0. So this means that this graph is non-orientable. So there's some, we found like a notion of orientability, and it turns out that we cannot really orient this graph this way. So an actual example is this tetrahedron graph. And it's now an exercise to check that we can pick a numbering of the edges, and there's no automorphism of this graph that maps it to 0 like we did with this one. So what you need to check is that all automorphisms act as an even permutation on the edges of this graph. So this has no because there's no automorphism that acts as an odd permutation on the edges. So this is a generator. So I call this object here, sorry, I forgot this, GC of G. And this is like the definition of this vector space. And of course, we consider these graphs and the labelings only up to isomorphism of graphs. So this is only for isomorphism classes. Okay, how am I doing with time? Good. So there's a obvious grading on GCG. So we just define K chains. So that's a subvector space of GCG. And this is just given by restriction to graphs with a specified number of edges. So we just restrict the number of edges of our graphs and take these as generators of our K chains.
Sorry, so in this definition, is it like for all automorphisms pi or all pi?
For all pi. Yeah. All permutations of these edge labels. And one thing that we can see is that this is a finite dimensional chain complex. So CK of GCG is 0 if K is smaller than G. So that's because if K is equal to G, so we have not enough edges to make this rank of this graph possible. So for K equals G, we have these kind of graphs that have only one vertex. And so they have the least number of vertices and the maximal number of edges. So these are these edges that these graphs that only consists of one vertex and a number of edges that are incident to this one vertex. So only loops. It's also 0 if k is larger than 3g minus 3. And this boundary comes from the constraint that we only allow 3 or minimal vertex degree 3. So here the saturation comes from graphs that have the most edges for a given genus or rank G. And these are 3 regular graphs. So for instance, we have these graphs, this one here, that saturate, that have the kind of largest number of edges. And then we can write down a differential. Or a boundary operator, probably better, boundary operator. So these maps, k chains to ck minus 1 chains. So it reduces the number of edges by 1 of these graphs. And the idea is very simple, that we map a graph with this orientation to the sum over all edges of the graph. No, again, wrote it wrong way. And we alternate with a sign that is given by this labeling, this ordering of the edges. We contract this edge, so it maps our graphs to the edge contractions. And we also take the ordering of the edges that is induced by the initial ordering in the natural sense. So in a way, this boundary operator models, it says that the boundary of a graph is the sum over all possible edge contractions of the graph. And we do this in a way compatible with this labeling of the edges. And now it's an easy exercise to check. So it follows from this that this is an actual boundary operator. This comes from this alternation over these labels. And this defines us graph homology. So this is then the homology in the usual sense, where we just mod out with the image of del, and we restrict to the degree k part of this quotient of vector spaces. Okay, so now triangulations in Pei, they were able to extract information from this graph complex that has been known before and transferred it to the cohomology of the modular space of curves. So there's also not so much known about this graph complex, actually, so it's kind of a mysterious object. So what is known about graph homology? The first thing is that there's a theorem by Wilwacher in 2015 that says that graph homology actually vanishes in a much larger range that is indicated by this observation that we have these kind of extremal graphs. So it's 0 already if k is smaller than 2g. So it's 0 very often if the number of edges is low is small compared to the rank. Wilbacher also proved a more interesting theorem, namely that if we take the sum over all g, and we have to start with 2, and we take precisely the homology group that is like the minimal non-trivial homology group of this complex, take the direct sum over all of these, then this direct sum actually can be equipped with a Lie algebra structure. So in this, in our grading, you can then see here that these are precisely the graphs where the rank is equal to 2 times the number of edges. So these are special graphs that also play an important role in quantum field theory. And on these kind of graphs, as we only look at graph homology on these specific graphs, then this thing here has a Lie algebra structure, and this Lie algebra turns out to be isomorphic to a very special Lie algebra, the so-called Brodendijk-Teichmüller Lie algebra. Which is a very mysterious object. But there's another theorem by Brown that tells us something about the specific Lie algebra from 2012, that there's a free Lie algebra living in this GRT Lie algebra. So he proved that there's an injection of a free Lie algebra that is generated by objects in rank 3, rank 5, and so on, these sigmas. And you can take all Lie brackets of these objects, and these inject. So each of these gives some generator of this GRT algebra. And this is also connected to the theory of so-called multiple zeta values. So it's a long story connected to so-called MZVs. But here again, you can use some combinatorics, which is nice. So you can count the number of generators that such a free Lie algebra has. And this is counted by the so-called Linden words. So the number of Linden words give like the number of generators here on this side. And what you can show from this is that as sort of a vector space, the dimension of this free Lie algebra in these sigmas, it grows more than exponentially at a specified rank G. So we have exponentially many generators here in this free Lie algebra. And now Chang-Gilles-Spain used the chain of arguments, so they took this result by Brown, they counted the number of generators of the free Lie algebra. Then they used this theorem of Wilbacher that related all these classes with the homology of the graph complex. And then they also proved their result that I deleted, that the graph complex injects into the cohomology of the modular space of curves. So this they generated, or they proved the existence of exponentially many classes in the cohomology of MG. And it follows from this that the dimension of a specific degree, so 4G minus 6 of MG q is larger than some constants to the power of g. And this way they proved that there's like exponentially much cohomology in this specific degree. And so this was a huge advance because previously there was only sub-exponentially much cohomology known of this modular space. So this was the first infinite family of the first exponentially growing family of classes. And of course, because it's exponentially growing, the number of these classes will quickly dwarf the number of stable classes that have been previously known. Right. And yeah, I should also mention that besides this, what's also known is some explicit calculations on this graph complex, and they have been done by many people, for instance, Barnatan, Bran Mackay, and also Wilbacher, and Brun over the years. And so you get a couple of more classes, a bit of more information on this graph complex that was just obtained by solving these equation systems that you get on a computer systematically. Okay. So this brings me to the question now, or the obvious question is, how far can this kind of chain of arguments from like these kind of things be expanded, this keyhole that has been discovered here, to resolve this initial dark matter problem on the modular space of curves? So how many more classes can we transfer from this graph complex into the modular space of curves? And this is like the new result. So the question is, how much more use can we get out of this specific injection that Cangelacious Payne applied so fruitfully? And so this is where like the results from the paper from last year, not so new anymore. And here the theorem is on the Euler characteristic of this graph complex. So you can investigate this question just as before Hara and Sergier did by looking at the Euler characteristic of the graph complex. So the Euler characteristic of the graph complex is just the alternating sum of the Betti numbers so let's say it like this first. But the Euler characteristic doesn't care if we compute it on homology or on the chain spaces. So we can just rewrite this as the alternating sum over the dimension of the k-chains of the space. And this is really a graph counting problem. So we have to count the number of orientable graphs with a specified number of edges and specified genus, and then take the alternating sum. So this is just the number of graphs that are orientable of rank G and with k edges. So because these are all the generators of this vector space. And yeah, the result is that this can be solved, and it can also be solved asymptotically. And the theorem is just the solution of this graph counting problem. So the Euler characteristic of this thing has a very interesting shape. So this is again a large G asymptotic, so large rank of the graph. And we have different asymptotics depending on the parity of G. So here's some constant, some other constant times G. And here's this G to the power of G minus 3/2. So this is G even. Then the odd G asymptotics, they are more complicated. So there's an exponentially growing term. There's also a sub-exponentially growing term. And then there's some more interesting function f of g, and some asymptotics that go like g to the power of g over 2 minus 1. And this is for g odd. And this function f of g, it has a very funny shape, so it's the cosine of pi times g over 4. And that would wouldn't be a problem to just have like a cosine in there of pi g over 4, because this just alternates somehow a bit and it's maybe 0 sometimes. But actually what you need to do is to take the square root of pi times g over 4. So now this function, it oscillates quite chaotically with g, because remember g is an integer. So, and then there's like more traditional terms here. So this is the theorem. The corollary to that, but it's not quite so trivial, is that the magnitude of this Euler characteristic here, it's actually growing like some constant times g to the power of g and some constant to the power of g over 2 for g even or g odd. So here it's modulated by g to the power of g over 2 and here to the power g to the power of g. But it's not so easy to get this bound from this lower, from this odd g bound because of this function f of g. The problem is that f of g become very small and cancel the growth rate of g to the power of g over 2. So this is because this function, even though it's never exactly 0, it can get arbitrarily close to 0. And the proximity to 0 is actually investigating like how close to 0 it can become, can be translated into a question on the so-called irrationality measure of pi. So this pi in here, it's obviously an irrational number, and its ability to approximate, so the square root, its ability to approximate a multiple of pi is a question on like this irrationality. And this, again, can be translated into the question, how small can this cosine can become once G is very large. And if it can cancel this huge growth rate that comes from the G to the power of G over 2. And thankfully, because this is a very popular constant, people have investigated this irrationality measure. And I was able to use some properties of this to show that this bound here actually holds. So this is quite nice about this, that you can apply these irrationality bounds in this context. Okay. Yeah, so I also want to mention that this is only like one part of the story. I focus on this part because it fits nicely. This is the modular space of curves. There are two ways to assign these orientations on these graphs. In this specific case, if you allow like for further generalizations, there's a whole zoo of graph complexes that compute other interesting things. But this kind of canonically dual kind of orientation of this graph complex can be tackled analogously, and it plays an important role in the theory of knots for so-called Vasiljev invariants. So there's an analogous story that you can say there, and this also shows that in this space of knot invariants and higher dimensional invariants, there's also lots of homology and graph homology. And yeah, so this also shows that this injection by Changelacious Payne, it actually transports like G to the power of G much cohomology into or information into the modular space of curves. And yeah, so the quantitative aspect of this, I maybe take the last minutes to show this with some pictures. So just explain everything that I told you now again with pictures, if possible. I don't know if I have. It works. Okay, so here's the picture of what was known before the pandemic on the cohomology of MG. There's no hockey stick or anything?
That's only the eye.
Okay, too bad. Okay, take this thing here. Okay, so here's the. So this is a picture of the cohomology, or what's known about it. The vertical axis shows the degree of the cohomology, and the horizontal axis, the genus of the modular space. There's something. Thank you.
Right button there.
Okay, great. And here I drew like this result by Hara, which is this dotted line, which is the maximal support for the cohomology. And here this blue wedge down there is the stable cohomology, which is known completely thanks to the result by Madsen and Weiss. Here in this big like shaded region, there nothing is really known, but this Hara-Zagier result that shows that everything grows with C times G to the power of 2G. So there's lots of stuff here going on where this question mark is, but these 4 classes here have been known before the pandemic. So this was the only thing that was known about the cohomology before the Changelacious Payne result. And here I also illustrated that this stable cohomology, it grows less than exponentially with some constants to the power of square root G. Now we can look into this, everything that was previously known about this graph complex. So here's a picture. Again, this wedge down here shows this result by Wilbacher that says that the homology, the graph homology, it vanishes if the degree is small compares to G. And then we have this pink line here, which is the line where this Grothendieck-Teichmüller, this mysterious Grothendieck-Teichmüller Lie algebra lives. And there are lots of classes on there, so it starts with one here. This is the sigma 3 class. This is sigma 5. This is sigma 7, and so on. And at the higher dots, we also have Lie brackets of these kind of classes, so they go like exponentially in number. And then these orange dots here, they are explicit computer calculations due to Barnatan, Wilwacher, and Mackay, Brian Mackay. The theorem now says that the analogous result to the Hara-Sergier story, that in this pink wedge that we see up here, there's also lots of stuff unknown. So in the pink wedge, we have this bound that I told you about, that there's super extra g to the power of g like growing homology in this complex for even g, and g to the power of g over 2 like growing homology in the odd g case.
Did you deliberately remove the minus 1 to the k?
No, yeah, so that was deliberate because this is so you can always estimate. So you can put in the minus 1 again, but then you would need this more complicated formula. But here I just took the magnitude, and of course, you can then estimate the total number of cohomology because, yeah. So in principle, there could be much more, of course. It's a very crude way to approximate a sum, an alternating sum. There's like many cancellations that are going on. Right. And now back to this picture of the cohomology of Mg. And here I can just switch on this injection by triangulaceous pane. So this is actually the wrong sign here, but it doesn't matter. So the homology lives inside the cohomology of the modular space of curves. And we get this now, this pink wedge suddenly also lives in this picture for the cohomology of Mg. And we see that this pink line with these dots up here, it lives exactly like below the top boundary of this cohomology. So what we learn from the new theorem is that also, of course, in this cohomology of the modular space of curves, there's a lot of stuff living in this pink wedge. And what I didn't mention is that there's also an algebraic geometric interpretation of this. So this injection, it's actually a bijection into the so-called top weight cohomology of the modular space of curves. And this graph complex exactly computes the top weight cohomology. So what this theorem says is that in this top weight layer, so you can also think of this picture as a layered picture where we have like an extra dimension coming out. And in a way, we know that this pink wedge here, it's the topmost layer of this cake that describes this cohomology. And we understand it completely via this graph complex and this topmost layer, this kind of frosting of the cake. We know that there's g to the power of g much cohomology now. But the negative result is, of course, that in the lower levels of this cohomology, we still have lots of stuff to find because this is growing like g to the power of 2g. So here we only have g to the power of g and g to the power of g over 2. So this is still only square root the amount of the total cohomology that is concentrated in this graph complex. And that can be explained by this injection by triangulaceous and pane. Okay, this is what I wanted to say.
Any questions?
So I know that in terms of finding explicit classes, the tough part is usually showing that things really are non-zero and exhibiting graphs that might give good classes is not so tough. But for you, with your explicit counting, do you get some reasonable guess, even if you can't show they're non-zero, of what some good classes might be?
Yeah, the problem is that the technique here really makes use that you can just replace the homology by the dimension of the chain spaces. And because you have an extremely alternating sum where you have extremely high cancellation, so everything cancels in the sum, almost everything. And this huge growth rate that you get is like the result of something that would grow much more if it wasn't for all this cancellation. You cannot really say if it's like if the graph homology is concentrated in a specific degree or anything like this. Yeah, so unfortunately this does not really tell you that much about the specific degree.
If you define the graph complex over the integers, does the homology have interesting torsion? And I guess this injection then breaks down?
What's the conjecture? Sorry, what breaks down?
I mean, and probably you don't inject into the integer cohomology anymore.
No, at least it's not known. So this work by Changaleshus-Payne, it very much made use of the rational coefficients. And yeah, so that so this also, yeah, no, I don't know of a version of this this Deligne spectral sequence that also works with integer coefficients and that could lead to something like this. But maybe there's.
No one else? Right, let's thank the speaker.